SB to SD. So the output is 1 0 and the weight is 1 because there is one number of 1. There is two number of 1 was present, so that's why the weight was 2. And here 1 is the weight of 1 0. Okay. And when I'm going from SD to SC, again 1 0, so weight is 1, so that's why x to the power 1. And when I'm going from SC to SA, so the output is 1 1. So this output is basically I'm writing from this table. Okay, so I've already seen you, and I've already shown you that this table I've just made this table, and from this table I'm using these outputs, the state transition outputs and corresponding the weights. Okay, so here the thing is that, so there is two possibility starting from SA and end at SA. So I've written here that, let me erase it. Okay, let me, okay, so paths starting and arriving at the all zero state SA. So we have to always starting from all zero state, okay, and end at all zero state. So path starting from and arriving at all zero state SA have a weight that can be calculated by adding exponents, that is I, of the x to the power I correspondingly for each possible paths from SA to SA. Okay, so it is basically saying that there is two possible path. One is this, that means SA, SB, SC, SA, and one is SA, SB, SD, SC, SA. So there is two possible path, right? So we have to add, we have to consider this path SA to SA, this two possible paths from SA to SA, and we have to add the value of i's. Like when I'm considering this straight line path like SA, SB, SC, SA, so what is the path gain? The all total path gain is 2 plus 1 3 plus 2 5. When I'm considering this path SA to SA, so this is 2, this is 1 3, this is 1, this is 4, and this is 2, which is 6. So 2 plus 1 plus 1 plus 2, so this is 6. And from the straight line SA, SB, SC, SA, this path 2 plus 1 plus 2, so this is 5. Okay, and you know that you can see from the diagram, you can compare from the traditional diagram to modified diagram that all self loop, okay, all the self loop is deleted. Okay, we have to delete all the self loop for any state. For any state we have to delete all the self loop. We will not consider any self loop. Okay, and then we will consider the rest transitions and corresponding outputs and weight of that output. Okay, so here it is, here we have got that there is two possible paths, and the straight line path containing the path gain as 5, and this path containing the path gain as 6, right? So this is the addition of i's. Okay, addition of I. So the thing is that this is SA, SB, SC, SA. That means you can see that SA, SB, SA, SB, SC, SA. So this is SA, SB, this path. Okay. So for this path, the path gain is 5, and from SA, SB, SD, SC, SA equals to 6. That means this path, SA, SB, SD, SC, SA. So okay. So for this path, the path gain is 6, right? So we have to consider the minimum path gain. So that is a minimum distance of the code is equal to 5. So that is my minimum distance of the code, minimum Hamming distance. You can say rather that minimum Hamming distance is 5. Okay, and it is also called the minimum free distance, that is D free. It is also called the D free. Why this is free? Because this is obstacle free path. You can say that the path consisting no any kind of obstacle. So that's why this is obstacle free path. So that's why this is called also the T free or TF. So TF equals to 5. So this is my distance, free distance, or you can say the minimum distance, minimum Hamming distance. So this is the procedure how to calculate this minimum Hamming distance from the state diagram. So you have to convert the traditional state diagram. You have to first make that table from the previous lecture. You have to make this table and you have to make this traditional state diagram. Then you have to delete all the self loops and you have to already only consider the output, the state transition outputs. Okay, these outputs, that is 1 1, this is 0 0, this is 1 1. Then you have to consider the weight of these outputs. Okay, so the weight of the output to be written at the power position of x, like when I'm considering SA to SB, the output is 1 1, so the weight is 2. So that's why this is written x to the power 2. When I'm considering SB to SD, so SB to SD, so it is 1 0, so weight of 1 0 is 1, so that's why this is x to the power 1. So in this way you have to write all the possible path gains and corresponding weights in the power position of x. So like x to the power I. Okay, then you have to add all you have to consider actually that what is the possible, how many possible paths are there from all zero state SA to all zero state SA. Okay, so from this diagram you can see that there is two possible paths. One is SA SB SC SA, this is straight line, and again another path SA SB SD SC SA. Okay, so you have to calculate the path gain correspondingly with these two paths. The path gain will be the addition of the value of i's. Okay, like from the straight line we will get 2 plus 1 plus 2, so this is 5, and from this path we will get 2 plus 1 plus 1 plus 2, so this is 6. So what were the when we will get the minimum path distance, so that will be our result. So that will be our D free, or you can say the minimum Hamming distance. Okay, so in this way we will calculate the minimum Hamming distance from the state diagram. Okay, or you can say modified state diagram. So now to see how to calculate the trellis diagram, you have to follow the PDF book page number is given, which is 180. Okay, I've already sent you the PDF. You know that the trellis diagram, from the trellis diagram, how we will calculate the minimum Hamming distance. This is very easy. So again you have to remember the previous lecture where I've discussed the trellis code, how to draw the trellis code, and this you will get on 180 page, that means page number 180, and this is the block of 6.10. so I've already prepared this book. So this is the thing. So this is the book. This is the book. So you can see that page number is 180. This is 180. So first of all, so this is the code trellis diagram. Okay, so this is the code trellis diagram. So from the code trellis diagram, this is very easier. Okay, so every time, you know that every time you have to I think you have already gone through the Viterbi code, how to calculate the Viterbi algorithm. So there we have considered that every time we have considered outputs. Okay, we have considered the outputs here in this position in above the arrows. Okay, so and we have calculated the Hamming distances between the received code in this position and corresponding output, and we have calculated the Hamming distance between this received code and this output. I think you can remember from the previous lecture. So that was from the